for two solids to be similar, all of their dimensions have to form the same ratio. All of their corresponding lengths have to be the same ratio.
What will be on the test?
Since they form the same ratio, you would say they are in proportion. Because remember, when you have equal ratios, you have a proportion. That proportion is called the scale factor. So the scale factor is a ratio of two corresponding lengths. Our theorem says what we can expect for the ratio of the perimeters, the ratio of the areas, the ratio of the volumes. That's what our theorem says. First off, think of perimeter or circumference as a length. Ratio of any two corresponding lengths is the scale factor. So if you're talking about the perimeter of the bases or the circumference of the bases, if you're talking a circle, then it will equal the scale factor when you put them in ratio. Just
Aren't all spheres similar?
all spheres are going to be similar. Yes. No.
Regular sphere.
If you have a square pyramid, they have to have the same heights in order to be similar. Yes, exactly. They have to have the same ratio for their heights as for their side. All of their lengths have to form the same fraction when you put them in ratio. Okay? So, always think about perimeters or circumferences as a length. Which means, by definition of scale factor, ratio of two corresponding lengths, the ratio of perimeters and ratio of circumferences will equal the scale factor.
Breaking my desk. Look at that. Breaking my desk. You need more staples.
If you look at my bottom left drawer, there are staples. Ratio of perimeters or ratio of circumferences of two similar solids will be the same as the scale factor. That brings us then to ratio of areas and ratio of volumes, and that's where our theorem comes in.
Volume is be the scale factor.
It is. And in general, we can kind of summarize this theorem by saying if the region is measured in square units, then the ratio will be a ratio of areas, because areas is measured in square units, and that will be the square of the scale factor. If
The amount of space that object and what dimension would take up, you got like area, volume.
we don't, because I don't think anyone really can even build something that is in a fourth dimension. So it's like theoretical type of science. If there is a fourth dimension, can you build something that, you know, is fourth dimensional?
Theoretically, there is a fourth dimension, but we just cannot, as humans, comprehend it since we live in the
And theoretically, you could argue that, but it is theoretical. So, moving to our theorem, Theorem 1211. If the scale factor of two similar solids is A to B, and then we're going to have two pieces here. Part 1. The ratio of corresponding perimeters is A to B.
It is skipped some here.
No. The sphere theorems of area and volume were the 12.8 and 12.9.
I don't know that.
You probably don't because you started using that reference sheet I gave you. Remember? Okay. So the ratio of corresponding perimeters is the same as the scale factor, is A to B. Part 2 now, and there are 3 parts here. The ratio of any two corresponding areas. Now areas would be square units in measures, so you square the scale factor. So it'll be A squared to B squared. And number 3, the ratio of the volumes. Is the cube of the scale factor. Now, using this, a few examples. I am going to look first off at page 511 and number 3. It tells me I have two similar cylinders with radii 3 and 4. When it tells me radii 3 and 4, that tells me the scale factor. The scale factor is a ratio of two corresponding lengths. So my scale factor is going to be 3 to 4. Then it asks me, part A, what's the ratio of the heights? I'm on number 3. Well, now I look at heights. Which does height fit? Is it a ratio of a corresponding length? Is it a ratio of a corresponding area? Or is it a ratio of a corresponding volume? Which one does height fit? Is it a length, an area, or a volume? It's a length. So it will be the same as the scale factor. Part B now. The ratio of the base circumferences. And again, it's a length, so 3 to 4. Part C now. The ratio of lateral area. Now it's an area. So which piece does it fit? We square the scale factor. So area 9 to 16. And finally, part D, the ratio of the volumes. And that would be the cube of the scale factor, which is then 3 cubed, 27. and 4 cubed, 64. Okay. Now we're going to use this to help us find a volume. So I am moving down to number 9. You're on number 9 with me. The package of a model airplane kit states the scale is 1 to 200. Now 1 to 200 being the scale means this is our scale factor. That's our A to B. Compare the amounts of paint required to cover the model and the actual plane. If I am talking about paint, is that an area or a volume or a length? It's an area. Paint means area. So I have to do A squared to B squared then, which is going to be 1, 2, and then squaring this. 1 to 40,000. Well, what about volumes? Then I would have to go 1 to 200 cubed, right? Now it also helps explain why when we were changing from cubic centimeters to cubic meters, why we had to divide by 100 cubed. Because if we're talking about going from 1 to 100 and you're changing to volume, 1 centimeter to 100 centimeter, when you talk about volume, is 1 cubed to 100 cubed, which is a million. So when you are changing from cubic centimeters to cubic meters, you have to actually divide by a million or by 100 cubed. What if we are changing from cubic feet to cubic yards? 1 cubic feet, and then compared to cubic yards. How many cubic feet are in a cubic yard? Well, there is 1 foot. There is 1 foot, or rather 3 feet to 1 yard. So if we cube this, there's going to be 27 feet cubed to 1 cubic yard. So if you're going to change from cubic feet to cubic yards, you have to divide by 27. It's the same idea. Okay. Now I want to do one more where we have to reduce and then find. And actually, I think I'll just let you do the assignment. I think we're good.